Okay, can I start? Okay. Yes. So, now this will be lecture 3. So, and I will discuss the effective approach to quantum gravity. And here, in principle, you can, yeah. So I will first tell about, some basic things about what means effective approach, which is a mainstream method in modern particle physics and quantum field theory. And then I will discuss qualitatively how we can make an application of effective approach to quantum gravity. And then I will concentrate on one particular problem, which is calculation of quantum corrections to the Newtonian potential. And then discuss some things which are like make a difference between me and other people, actually. And I would say that if we decide by vote, I will lose. Okay, but things are not decided by vote, so I believe that I am correct. And then the last part will be this. I will show you some approach based on geodesics and how to achieve invariant result in the part which is more or less safe. So this part is was developed by Dalvit and Massitelli in this paper in '97. Dalvit is now at that time I think he was student of Diego Massitelli, and now he is in Los Alamos. He is head of the group working on Casimir effect, and Diego Massitelli is in barylogy here, not so far. So yeah. Then I will use some logic which was developed in this paper, polemic notes on quantum gravity. These two papers I will cite a lot. And then we recalculated with Tiberio de Paolo Nieto and Leonardo Modesto. We basically repeated the paper of Dalvit and Massitelli, but in a little bit different way. But in principle, it's very close. And then I cite here the lecture notes of Tiberio, which were unpublished. But if you go to the handbook, okay, there is some review paper by Tiberio and Brennevicini, which includes this part according to Tiberio. So it's available. So what is the standard reading? Once again, about quantum gravity part, you can start with this book because it's textbook. Then there is this classical papers by Donahue. All this effective approach to quantum gravity started from these two papers in Physical Review Letters and Physical Review. I would even say that these Physical Review Letters is the most clear. Okay. Then it attracted a lot of interest, so it became one of the mainstream approach in quantum gravity. And so Cliff Burgess has this Living Gravity's Relativity. It's a kind of a book. Okay, you can use this. And then there is a special section in the handbook of quantum gravity. There is a special section of effective quantum gravity, which was edited exactly by Burgess and Donahue. And there are many papers, actually, review papers by people working professionally on this, not like me, because I'm an amateur, kind of amateur. So there are people who make very different things. But I will concentrate only on formal part, and will try to show you only this formal corrections to Newtonian potential, as I think it should be done, and like Massitelli thinks the same, I guess. So, and by the end, I will show you something which was never published, that how it can be extended, and maybe this is interesting. I'm not sure that here are many cosmologists, but if there should be some cosmologists, they could be interested in this. So, the original paper, as I said, which I will follow, will be this one, Dalvit and Massitelli. The whole game is that you have the tree-level diagram, which it gives you Newtonian potential. It's some textbooks thing. But if you want to calculate one-loop corrections to it, then there are different diagrams, and you may use all these diagrams or part of these diagrams. Depends on you. And in all these cases, you have to fight with these ambiguities coming from choice of gauge fixing, parameterization, and so on. So, in some cases, you are working effectively with amplitudes. part of the S matrix. And S matrix is supposed to be independent on parameterization and gauge fixing. I'm not sure that it applies directly to the effective approach, but in principle it should be like that. So and in the Dalvit and Mazzitelli approach, we just intentionally throw out part of the diagrams and then fight to have invariant result, which I will show you. I think it will be the simplest structure in this part because you will understand how it works. So what is the effective approach? Effective approach is something you learn from high school actually, without understanding this. What I mean, when I give lectures on first physics, the classical mechanics for beginners, I always do the following. I take a piece of chalk and throw it, and it lands. Then I tell students, look, in order to describe this motion of this piece of chalk, you just need Newtonian mechanics of the point-like particles. Okay, I am author of the textbook on classical mechanics or Newtonian mechanics before Lagrange equations. So I know what I'm saying. So you need just Newtonian equations for the point-like particles. So you don't need many things. When you throw this piece of chalk, you forget many things. You forget that the piece of chalk may rotate because it does not affect this, essentially its trajectory. But if we think more, we actually ignore many other things. For example, a piece of chalk is made out of molecules. And these molecules have its own motion inside the piece of chalk, right? The molecules are done from atoms. Atoms have motion inside molecules, and moreover, they interact with atoms in other molecules. We ignore this completely when we throw a piece of chalk. You look at me and think it's strange what he is saying. Nobody does this, of course, and we should not do it. But then, inside the atom, there is a nucleus and electrons. Once again, we ignore it completely. Inside each nucleus, there are quarks, gluons, and so we ignore it completely. Why? Why we can do it? Why we don't need all this to describe the motion of the piece of chalk or any other macroscopic object? The answer is the following. In order to wake up these levels of physics, which correspond to atoms, molecules, protons, neutrons, and so on, we need much more energy, which is available when you throw out the piece of chalk. Actually, if you take all energy in the piece of chalk, you can destroy the town. Okay, it's a lot of energy inside, but we don't use it. We just put some kinetic energy into the piece of chalk, and due to this energy, it flies. Very good. Then, we have a lot of examples of this sort in physics, like when you calculate atomic spectrum. Okay, you don't need, let's say, simple example of the spectrum of the atom of hydrogen. You have it, you compare to experiment, and it's perfect, okay, or almost perfect. And why? We know that in fact this problem assumes that a point like electron, quantum object, okay, flies around the center. But we know that the center is the nucleus of hydrogenium. It has size, it has its own angular momentum, it has internal structure. Once again, it has quarks, gluons, and so on. Why we ignore it? Because once again, we don't need to wake up these degrees of freedom. We are perfectly well with motion of electron around the point like nucleus. So, and this is like standard thing. So in each of these examples, every time you meet, you can consider that you have at least you have two energy scales: one ultraviolet scale and infrared scale. Okay, when you deal with the phenomena at the infrared scale, you don't need to worry about ultraviolet scale. Okay, and this is actually the effective approach. It looks like something primitive and obvious, but in quantum field theory, it's not that primitive and not as obvious. And if you take like the paper of Manahar, which I mentioned before, then you see that it's like technically complicated thing in quantum field theory. So the idea was introduced by Steven Weinberg in the 70s and became, as I wrote here, mainstream quantum field theory framework. And every time, what it means basically, it means that every time we consider physics of some restricted class of phenomena, and we don't care of the rest of the physics. So every time we try to have theory of something, okay, and don't try to make theory of everything. That means pick up all phenomena at the same time, because this would be something impossible to do. So, for the classical examples are Fermi theory of weak interactions. You know that it works with the 4 fermions interacting in the same point. This theory is non-renormalizable, okay, by power quantum. So if you treat this theory at quantum level and start to calculate loops, you will see that there are contour terms which are far, far beyond the classical action. And with each loop, you have more and more contour terms. So theory is badly non-renormalizable, but we don't need it. We just take it at the tree level, calculate our things, low energy, things related to weak interaction, and it's perfect. Okay? Then inside this thing which we calculate, there is W and Z boson, as Leche Lopez introduced many years ago. And and this gives you, when you don't come to the energy comparable to the mass of W and Z, that means if you work below, let's say, 1 GeV, then you will never ever observe W and Z. You will only see Fermi interaction. The same with quarks. With quarks, you need QCD, but in low energies, you don't need QCD. You can work with so-called chiral perturbation theory, or you can use Nambu-Ioannolo-Zinio, which is a phenomenological model of quark interactions. So it's very good, it works, it gives you the result, and you don't need non-perturbative QCD, which is a complicated thing. So the minimal standard model itself is an effective theory, because after the discovery of mass of the neutrino, we have general opinion that minimal standard model should be extended somehow. And people expect that the ultraviolet completion of minimal standard model can be something complicated actually. Maybe grand unification theory, maybe Patti-Salam, maybe something else. We don't know. But we can make calculations in minimal standard model at tree level, at loop level, and in principle, the output is very, very satisfactory. It fits everything we can see in the accelerators. So, can we apply this to gravity? It would be very interesting because, as we know, in gravity we are in the situation like in the description of weak interactions before Leche Lopez. So we have the theory of Einstein gravity, which is non-renormalizable, and we don't have perfect ultraviolet completion. As I explained in the first lecture, if we have this completion, it's going to be complicated. So it's probably will not be simple. Okay? If you go to string theory, which is another way to make ultraviolet completion of string theory of relativity, then it is very complicated theory. You may like it or not, but it is very complicated, very beautiful, very complicated, mathematically rich theory. Okay? So it's not going to be simple. But we want something for low energies. And we know that high energy effects in quantum gravity are somewhere close to the Planck mass. So it means that it is like 11 orders of magnitude above our anything we can have experimentally. So the question is why we need to worry about Planck scale. We better think about something which we can measure someday, if not today or tomorrow, right? So this was an idea of Donahue. He tried to construct, because Donahue is a very famous expert in minimal standard model and not minimal too. So he tried to apply this idea to quantum gravity. And once again, typically in the effective approach, we have two different scales, ultraviolet scale, infrared scale. Then when we work in the infrared scale, we don't need to worry about ultraviolet scale. What it means from the practical point of view. As I explained to you, there is a so-called Weinberg theory, which was proved by Steven Weinberg in about 65, so it's 60 years ago. But in fact, it was known even in 50s, but without proof, and people understood this. That divergences, ultraviolet divergences, correspond to the local terms in effective action. Okay? From the physics side, it's completely obvious. Why? Ultraviolet divergences means the limit of high energies. According to quantum mechanics, high energies means short distances. So short distances means that there is no way to apply here non-localities. Non-localities is something which connects points with big distance, right? So, so the ultraviolet divergences are local. If they are local, okay, then in principle, what we need for the infrared is something non-local, like these logarithms which we discussed, okay, or something else. So when we look for the non-local contributions, okay, which are non-logarithmic especially, we can forget about ultraviolet. Ultraviolet terms are local, so they do not contribute in the infrared. Okay? So this is an idea. And we know that if we have some physical observables and they are related to the non-local form factors, then the relation between ultraviolet divergence and non-local form factors in the infrared is lost. So we don't need to worry. Maybe there are some ultraviolet form divergences. Of course there are. Maybe there are some logarithmic divergences in the momentum scheme. Certainly there is something. We don't know how to deal with them, but we can try to extract the non-local, interesting for us, non-local infrared effects from the effective theory, which does not care about the ultraviolet complexion. Okay? So, and in the first lecture of today, I show you that in principle, we have some indications that whatever is the complete theory of quantum gravity, in the infrared we probably have to deal with the Einstein gravity. And if this is true, we have the next question: how we calculate, how we can extract this physical observable from the effective quantum Einstein gravity. And the first question: can we apply this to quantum gravity? And Donahue, in several papers, because after these two first papers, he wrote many lectures you can find in the archive easily. Like there is like 2 dozens of review papers, lectures, and so on. Everything very nice, and you can go directly to the handbook of quantum gravity and see everything there. So in quantum gravity, as Donahue said, we have absolutely perfect example, best possible example of the application of effective ideas. Why? Because here we have only 2 scales. The high energy scale is Planck scale, 1019 GeV. As we already know, this is the maximal possible energy we can imagine. We basically don't care about what happens in the trans-Planckian area, okay? We may think that there is some cutoff in physics, natural cutoff for the density of gravitons, which never accumulate with the Planck density. So it is maximum possible energy. And in the lower energy scale, we have graviton, and graviton has 0 mass. Of course, in this universe, it's very difficult to have 0 mass. Exactly 0 mass. Why? Because the universe has finite size. It has the size of horizon. Okay? Between the horizon, one side of horizon and another side of horizon, there is a finite distance, the size of the universe. So if we take the particle which has this constant length, then we have 10 minus 42 GeV. It is the Hubble constant, Hubble parameter of today. So this is the lowest possible energy you may have in this universe. And the separation between these 2 scales is about 60 orders of magnitude. And it is the maximal possible separation you can imagine as a physicist. Okay? You know that mathematicians have a number, Google. It writes a little bit different from the Google we all know, which means 10 in the power 100. So it's the biggest possible number which students or humans can imagine. Actually, it is not true. Once I was verifying the entrance exam in university, and these candidates, were asked to calculate the orbit of the Jupiter, and one guy gave the answer 10 in the power of 2,900 kilometers, which is a really big number. If you divide it by Google, it doesn't change. so because we made a bet who will have a bigger number in this game. So, but it is some exotic situation. So in a normal life, 60 orders of magnitude is a lot, okay? And this is basically maximum you can have in particle physics. Okay, so you are supposed to have here a perfect separation between ultraviolet and infrared. So we really don't need to care about ultraviolet compression when you make calculations of physical things. For example, if you are dealing with inflation, inflation corresponds to the energy 10, 13 GeV or something like that. So this is maximal physical thing we need. So still you have 6 orders of magnitudes below Planck mass, and this means we are very safe, much better than electroweak or some other cases. Good. So Donahue made this heroic first pioneer calculations in these 2 papers, and there is a subtle part in this, because when you calculate first correction to the Newton law, there are 2 terms. One is, Newton potential is 1 over r. But these first corrections can be 1 over r squared and 1 over r cubed, right? And you have also relativity, and relativity gives you relativistic corrections. And the first correction, this is post-Newtonian approximation, ppm. So first correction is exactly 1 over r squared. This is something very, very well verified experimentally. Okay, if you take the book of Clifford Wheel about the test of relativity, also living gravity relativity, then you will see that this coefficient the number is very, very well verified. It's, if I'm feeling not wrong, it's like +2 or something. So when you calculate quantum corrections, you know the answer. It has to be this +2. If you get +3 or -5, it is a disaster. It means that you proved that gravity cannot be quantized at all. Nothing else, nothing more. So Donahue got this number in these first papers. But then people started to find mistakes in his calculation. First was this Humber-Liu, Muzinich-Vokus, they, Akundov, Bellucci, Sheikh, they basically found that the sign of one diagram was changed. Then we found in this paper with Halael, Nieto, and Penafirme that some diagrams which Donahue decided not to include. If you don't include them, then it's not part of amplitude. So the result starts to depend on gauge fixing. And this is bad, because if it doesn't depend on the gauge fixing, then you can have whatever you want. But the, let's say, merit of this is basically 0. So then Dalvit and Mazzitelli, before us, they did this calculation, and they just said, okay, all these diagrams which gave problems should be abandoned. You don't need them. And then I thought about this. I did not know about paper of Dalvit and Mazzitelli, so I noted, but I didn't take it serious. And I wrote this paper and said the following: that some part of the diagrams really have to be ignored, and others, some other questions like universality of quantum gravity and so on. Finally, Bjerrum, Bohr, Donahue, and Holstein made this calculation without mistakes. And Kriklovich and Kirillin, Kriklovich is a very famous man who first calculated wave function for the Yang-Mills field in '68. Okay, 5 years before Gross-Wilczek and Politzer. So, but he did not realize that this gives asymptotic frequency. That's why he did not get Nobel Prize. So, yeah. So he knows how to calculate diagrams, at least believe me. So these 2 groups calculated all these quantum corrections, and according to what Donahue told me last time, they had an agreement. So actually, even before Donahue, this was calculated. All this was calculated by this Japanese gentleman Iwasaki in 71, 23 years before Donahue, when I was in school. So Iwasaki already calculated these diagrams, and actually he did not think about effective quantum gravity. So he calculated much more than Donahue and all these people. He calculated contributions from scalars, spinors, and vectors, massive vectors, and all of them gave different results. It's strange, but it was so. So you will see in the next transparencies what it means. So we have a trouble, because it means that gravity is not universal. Okay, you describe your matter by vectors or by spinors or by scalars, and you get different results, which is something we are not ready to. Very good. So what is the story? Why you have to put some diagrams in and abandon other diagrams? To understand this, let us go back and think how we quantize gravity. So we quantize gravity in a standard way. We start with this theory which has Einstein gravity. This time we don't need cosmological constant because we need Newton potential. It means that we are at the astrophysics scale in the best case scenario. And cosmological constant is so small that even inside the group of galaxies it almost does not manifest. So Newton constant, Newton potential works, let's say, in solar system, in galaxy, if you want, okay, but not at the scale of universe. Well, there are some papers about this too. So what you have here is the following. You use Faddeev-Popov prescription, DeWitt-Faddeev-Popov prescription. So you put your H-fixing action. There are two arbitrary parameters, alpha and beta, as we already know from the first lecture. Then there is a cost, of course, okay, and matter. Donahue described matter as a minimal massive scalar field, okay, and then his purpose was to find interaction potential in the static limit between two masses, m1 and m2. So, in principle, if you take like textbooks like Test and Schroer or things like that, they have this example only for QED, and the difference is not big. So you actually, once I tried to make this calculation, it's not so simple either, because once I tried to make this calculation without anything, just took paper and started to do. Then I found that I cannot do it. So finally I took books, I took Donahue papers, and I did. But it was not easy. It was not easy at all. It's very good exercise for students. You will learn something about this and about yourself. So don't be too much self-confident. Huh? So, but anyway, if you do it correctly, okay, the main problem is the following. I will explain. So you have two static fields. It means that momentum is here 0, here 0, here 0, here 0. Then this momentum of graviton, which makes this exchange, is also 0. But if the momentum of graviton is 0, then it gives you singularity. So you don't know how to calculate what you integrate. 0 or 1/0. It doesn't work. So you need to be very smart and remember that this graviton is not on shell. Very important. That when you integrate intermediate particle, it's not on shell. If you understand this, the rest is actually not that complicated. So finally, you calculate this part of the rest matrix, the interaction part, make Fourier transform, and you get your Newtonian potential. Very simple. Well, up to some technical details. Okay? Very simple. You get Newtonian potential, we can be happy. Now the next question is how we calculate one loop corrections to this. Okay? And this is the subject of almost all my lectures. So Donahue identified that, by the way, one detail. Actually, what is the role of R here? The role of R is simple. You see, this, if you go to the static limit, then K goes to 0. Okay? K goes to 0. When K goes to 0, you have infinity. Infrared, it's infrared divergence, not ultraviolet. So you can, and randomization doesn't help here. But since the distance between these points is finite, it's R, so this integral has a natural low energy cutoff. Okay? And so R here enters as a low energy natural cutoff. It's not cutoff you put to regularize divergence. It just kills divergence for you. Okay? From physical point of view. If you have questions, please ask me. So the question is how we find corrections. And when you have corrections, we find that there are two types of integrals in the diagrams. One is what Donahue called p-type terms. So p because from the polynomial. So you have this kind of infrared divergences. Okay? Then you take into account this regulator, infrared regulator, and make Fourier transform, and you get this. And others are L-type divergences. L is from logarithmic because here you have log. Once again, you make this, both are of course infrared divergent, but if Q goes to 0, here you have log of 0 and here you have 1/0. So in both cases, in this case you get 1/r cubed. As I told you before, this term gives you contribution of 1/r squared, which is exactly repeats the form of the first ppn contribution. Okay, so this is experimentally verifiable. This is very, very far from it being experimentally verifiable. There are like more than 70 orders of magnitude difference between experiment and theory. So what I will try to convince you is that this has to be omitted, disregarded, and we leave up with the part which is irrelevant. It's not a good news, but it's true. So those are diagrams which contribute to the L terms. These diagrams are done from the loop of massless fields, in this case just gravitational field. It's not exactly graviton because we use Faddeev-Popov, and then graviton is the traceless transverse mode, right? Tensor mode. And here you have contribution of all modes, scalar, vector, and tensor. But you have these three types of diagrams. This, of course, also there is the ghost contribution here, which I did not put because I wanted to have it beautiful in one line. So we have here what we have. So these diagrams are very easy to calculate, relatively easy to calculate. They give you logarithmic type of divergence in the infrared. Okay, they give us irrelevant contributions, phenomenologically irrelevant, not theoretically, contributions to corrective Newtonian potential, and this we can do. Moreover, as Galvin and Mazzitelli explained to us, we don't need to calculate diagrams. We just can take these, restore these diagrams from the effective action, which we calculate by heat kernel method. So actually, to derive these things, we don't need to work too much. We don't need diagrams at all. We can do it immediately. I will show you at the end, closer to the end, how it's done. It's very easy. Well, not completely simple, but after Dalton and Mazzitelli, it got easy. So this is part which is safe. Nobody complains against these diagrams. But there is another set of diagrams, this one. And those diagrams, they have internal lines of massive scalar field. This was exactly the diagram which Donahue omitted in the first work, okay? And then people convinced him to put it back because otherwise the sum of the diagrams does not represent the part of the S matrix and starts to depend on the gauge fixation on alpha and beta. But even if we do this, there is a doubt. Should we include these diagrams? Let us think a little bit. What means that we have internal lines of massive scalar field? This means that we quantize massive scalar field. Internal line means quantum field. External line can mean external field, right? External source in this case. But internal line, no. Internal line means that you have quantum field. What is our purpose? We want to find interaction between Earth and the Moon, or Sun and the Mercury. So what it means that we quantize Moon, Sun, Mercury, and Earth. Can we quantize Moon? Some people say that it's dangerous. I, for example, don't like to quantize Moon, because Moon can quantize you back. Okay, so, now people don't believe that this Catholic University, but there was time when people were very careful with quantizing Moon and things like that. so we know that. So maybe it is not true, but in principle it's good to be careful. So anyway, the astronomic bodies which are participating in the Newton interactions, or in the laboratory lab now in Southampton, they have an experiment which measures Newton corrections between very small pieces of metal with a completely fabulous precision. So all these things are macroscopic. What it means? It means that they are produced from the baryonic matter. What is baryonic matter? Baryonic matter certainly is not a scalar field. It is done from fermions, right? As we all are done from fermions. But they are not fermions. Fermions are bonded to some bonded particles. They are not elementary fermions. If you take the baryonic mass, and remember that it is done basically from neutrons and protons, then remember that the mass of the neutron and the mass of the proton is not the sum of the masses of elementary fields like quarks. Gluons are masses. So the 97% of the mass of the proton is the energy of interaction, which we observe as mass because mc squared is the rest mass. But energy, E, includes the you call it conformal anomaly or whatever. You can, from Newtonian mechanics point of view, it's just potential and kinetic energy of particles. And you observe it as a mass. What it means? It means that all this is quantum. And then if you consider the expansion in h bar, then of course this was my argumentation in this procedure. So if you consider this as expansion in h bar, then baryonic mass is something which is already proportional to h bar. So you cannot treat it baryons as baryonic mass as something classical in this framework. So in order to describe macroscopic bodies, you need some other formalism. And the most obvious thing is just to leave Moon in peace, do not quantize it, and keep it as an external classical source, and quantize only graviton. And this is exactly what Dalvik and Mazitelli did. So we don't need to go far, we don't need to work too much. Mazitelli and Dalvik did it for us. So another argument to drop these diagrams is this Casimir effect. Casimir effect is the energy of vacuum calculated, for example, for two parallel conducting plates. It's a classical example. Until 3 years ago, people said that it was reproduced in experiments with a 1% mistake. Now some people, Lamoureux and others, say that maybe it's not true, I don't know. So, but the standard point of view is that it works very well. And when you calculate Casimir effect, you basically do not quantize the source. You do not quantize your parallel plates. You just quantize vacuum between these plates. Okay? This is exactly what you have to do here. Okay? Also, there was some unpublished work in Germany many years ago, in early 70s, when the guy wrote diploma but did not publish it. When he calculated Casimir effect between electromagnetic and gravitational, between 2 point-like particles, and found that this is exactly the result of QED, without quantizing particles themselves, of course. Okay? But for gravitons, it was never done. It would be interesting thing to do, by the way. So we have this, and so it means that we have to drop all these diagrams with, if you follow this logic, don't know if you disagree completely, okay? Then you have to drop these diagrams with internal lines of massive fields. Good. Then the question is, if we do not drop the diagrams with internal scalar field, then we are in the safe situation. In principle, if we make calculations correctly, then we work with the S matrix, and the S matrix is gauge fixing independent, parameterization independent. We don't need to worry about it. At least in the normal quantum field theory. About effective, I'm not 100% convinced. But now we drop part of the diagram. So how we can ensure that our result does not depend on the gauge fixing? Once again, we have alpha and beta, which are parameters of the gauge fixing. And also we have the same as before, parameters of the parameterization, as I showed you in the first lecture today. So Dalvik and Mazitelli, they worked with alpha, if I'm not wrong, and checked that the result in their way does not depend on alpha. We worked in this paper with gammas. Technically, it's more simple, actually. And we have shown that also it does not depend on gammas with their method, with the method of Dalvik and Mazitelli. So how it works? You don't need scalar field. You just let's take a classical source in the form of particle, point-like particle. We all know that the action of point-like relativistic particle is like this. Here, the speed of light is 1. Then we start to take variational derivatives. First variational derivative gives you energy momentum tensor for the point-like particle. Second variational derivative gives you this. Okay? And now we need to derive quantum corrections. Remember that we quantize only gravity. So it is something opposite to the semi-classical gravity. In semi-classical gravity, you quantize matter and do not quantize gravity. Now you quantize gravity and you do not quantize matter. Okay? It's another physical situation and another purpose, and so we have to do this. Now, we need this to work with this standard expression for the effective action, one loop effective action. So it's trace log of h. It is the so-called Hessian people use. When I was young, nobody called it Hessian 40 years ago. so now everybody calls it Hessian. And this is the bilinear operator of the ghost. Okay? So we have with this arbitrary parameterization, we have this expression. Now, everything goes like in this classical paper of Hoft and Feldman, which I mentioned in the first lecture yesterday. So until you add this. This is the contribution of external particle source. Okay? External particle source. Very good. Now, since our matter is not arbitrary, it's point-weight particles, then we can use this, find and verify this relation. So the trace, the contraction of m of this Hessian of the particle is exactly 1/4 of the t alpha beta. Square of this guy is the square of the energy momentum tensor, and the square of the energy momentum tensor is the square of its trace. So the trace is like this. So these formulas make calculation of this expression trace log h quite simple. And ghost does not change. So you just take the results from quantum gravity. If we make this calculation, we get the result. This is the result. As we know from the previous lecture, we have c squared, we have r squared. As usually in Einstein gravity, we don't have divergences of the r type and cosmological constant. It's impossible by power counting. But since we have external energy momentum tensor, we have these three new terms. Beta function for RT, T is the source. Second beta functions RT for traces, and T squared. So these are divergences. Now these formulas are huge. I put here only part of it. If you go to our paper, you will see that they take like 5 pages. So they're huge formulas with a lot of gammas everywhere. So the dependence is very complicated. Okay, I was actually surprised when journal agreed to publish it, because usually journals don't like to publish pages of formulas. 20 years ago it would be impossible. Now they don't care too much, but in principle, it was like that. So there are big formulas, and what is important is that we expect that by the end of the day, all these formulas will cancel, and we get the result which does not depend on gamma. At this stage, it looks strange. So let's make a first check. So we take this expression, once again I repeat the same formula, and then we use here this on-shell condition, classical equations of motion. What happens? All dependencies of gamma disappear, and we end up with this formula. The rest cancels. Is this formula what we need? Absolutely not, because we don't need this formula. We want to calculate the interaction between two sources, and here is like contact interactions. It's not a correction to the Newton force. You understand, right? So this is like product of two particles in the same point. So does not give you any interaction between these particles. Only this is non-zero. Only if these two particles have the same position. Makes no sense. But technically it's nice, because we see that this formula is correct. At least it passed one single test. Now, how Dalvit and Mazzitelli did? They started with divergence, and as I explained to you in the first lecture today, just map it to logarithm. Because we have massless particle. So divergence corresponds to this primitive logarithm. So we don't need to calculate diagrams. We immediately get our one loop effective action, the finite part of one loop effective action. And basically it's all one loop effective action. Okay, we have nothing else. But once again we have to be careful, because all these coefficients are ambiguous. Okay, all these coefficients are ambiguous. So now we meet the next challenge: how to extract physically interesting result from this ambiguity. Okay, and let me show you how the same thing can be done without effective approach, so that you can compare. Without effective approach, people made it a lot, starting from Stella paper of 78. Okay, So let us go beyond Stella and put this theory with arbitrary form factors between Riemann tensors, Ricci tensors, and a scalar. F1, F2, and 3 with tildes are arbitrary functions of box, divided by some mass square just to keep normal dimension. So first of all, you can prove that this combination gives you R cubed. If I remove this F, it would be Gauss-Bonnet. So, okay, it's obvious. But even without Gauss, with boxes, it gives proportional to R cubed. For the functions F, which can be expanded into series, we did it in the paper with Asore in 97. And for the general case, I took it from these Tiberius lectures on effective quantum gravity, which were not eyesight, exactly for this reason. So it means that we can eliminate this guy and work directly with two remaining form factors, so we have this formula. This is the most general thing you can have in gravity if it concerns the quantum not quantum, just interaction between two particles. Okay, you absolutely cannot have metric-dependent gravity which goes beyond this formula. Any theory gives you this. Good. Now we want to work it. How will we do it? First of all, we make the same linearization as before. So we take metric equal to Minkowski plus h mu and linearize the corresponding equations of motion. What we get? We get these two form factors, A1, A2, multiplied by these tensor structures. Okay? And this is a third combination of the same two form factors, and it gives you 1/2 T min. Okay? This is linearization. This is an exercise you can do. Remember that in the linear approximation, F1 of box becomes F1 of flat box, of Minkowski box. So H mu is only at the first order here and the first order here. All the formulas, intermediate formulas, you can find and check if you want in our book with Bookbinder, or even better in the review in handbook. I made a little bit better. So these functions A1, A2 are related to F1 and F2 in this way. Remember that we are not now working with an effective approach. We just take any F. I want to show you how it works. Now, we take this. This is what we want. It is a static limit in which we need for Newtonian interaction. Cosmologists call it conformal gauge. Okay, because in cosmology there is a science called cosmological perturbations, so they call this phi and psi conformal gauge. We just take two arbitrary functions of r, of the distance between two points, two charges, and so we want it static, so we replace box by minus Laplace operator. Good. So for after very small algebra, we get these equations for phi and psi. So you see this is not horribly complicated. When we have this, we have to solve it. Actually, if we do it for effective method, it will be absolutely the same equations. But the way of solving this is different. This is what I want to emphasize. So if we take just GR, then it's easy to see that we get phi equal to psi, and they give you perfectly well your Newtonian force. Okay, for GR. For GR, this method works exactly and gives you the same as before. Now, what we will have for more complicated theories. So it's interesting, by the way, that if you want phi equal to psi, then you have to assume that these two form factors boil down to one single form factor, and so you put here Einstein tensor and here R minimum. Some people working on non-local gravity say that this is very important. I never could understand why. So for me, it's the same thing, but technical detail, I think. Now we write phi and psi in this way using Fourier transform. Okay, and then these two new functions f2 and f0 are combinations of A1 and A2, and this is how it is because some part is related to c squared, some part is related to r squared as usual. Then, if we take real part of this exponential, then we get this. Okay? And now we have to take this integral. This is not really difficult for many different theories, and we get the following result. For example, for Einstein gravity, as I said, you get phi equal to psi Newtonian potential. Perfect. Now, for force derivative gravity without effective approach, you get here Newtonian term, and then two corrections. These two corrections correspond to Yukawa interaction. They correspond to the mass of the spin 2 particle and the mass of the spin 0 particle. Okay? Actually, M2 particle is a ghost and M0 particle is not a ghost. So here you have 1 minus 4 third plus 1. It means that in the R equal to 0, this singularity, Newtonian singularity, goes out. You don't have it. For psi, you have 1 minus 2 thirds minus 1 third. Once again, you have no singularity. This was observation of Stella in 78. That this singularity, Newtonian singularity, disappears in four derivative gravity. Breno-Guccini has some theory that in any higher derivative theory, even non-renormalizable, because higher derivative theory can be badly non-renormalizable if you put different number of derivatives in the spinor sector, tensor sector, better say, and scalar, then it is horribly non-renormalizable. But still, you don't have this singularity. Singularity disappears. Very good. So with 6 derivatives or more derivatives. So if you have it, if you have higher derivatives, then you don't have singularity. Very good. But this is without effective method. Okay, this without effective method. So you see here, you have correction to the Newtonian potential, but this correction works only in the very, very short distances, close to R, because M2 and M0 are the Planck order of magnitude. So only in the Planck distances you will see that singularity disappears. Okay, in the big distances you see nothing. Okay, this is not what we want. We want to use effective approach exactly in the way of Simon and Parker and Simon. What it means? It means that we shall solve the same equations in a completely different way. Okay, now once again, we have this effective function. Now with our terms, with t mu, and so on. And now we have these particular form factors. We don't have any function. We need our function, okay? With log of log and extra box because it comes from R squared and R mu squared. So once again, we put this, we make this choice for our H functions, for our metric perturbations, requires that we are in the static limit, and take this special formula for the TBE, which gives us these formulas which we know, and then we have these equations. And these equations, most important, we solve considering these log terms as small perturbations. So we do not solve this equation, we solve them perturbatively. This is because we want to work with effective approach. Okay, it could be possible, perfectly possible to solve them exactly, but this is not what we intend to do. And then we have completely different solution. We have phi and psi equal to 0. 0 is Newtonian by definition. Plus correction, phi 1 and psi 1. If we do this, we have this phi 0 and psi 0 is what we expect. And then we have this phi 1 and psi 1. Okay? Please note that these equations are not complicated because here you have for psi 1 and phi 1, you have linear equation because right hand side is completely known and it's Laplace. So you just go to Fourier, make Fourier transform and integrate. So technically it's not difficult to do. Okay? And gives you this result. So this is phi 1 and this is psi 1. Should we be happy with this? No. Why? The reason is the following. These combinations in these parentheses here and here are still dependent on gammas and betas. They are not physical results. They depend on gauge fixing, they depend on parameterization. If you write these two formulas explicitly, they will take pages. Gammas and betas did not cancel. So what we do? I don't know. we say this is the answer. Okay, this is our answer. Very good, but this is not what we want from our answer. Okay, so if we remember that kappa square over 16 pi is g, this is exactly Newtonian term, right? But then we have second term. Second term is gauge fixing and parameterization dependent. And here we have to invoke what did Massitelli interpret. But before that, let me make the following observation. If I go to minimal parameterization, very simple, and to special choice of gauge fixing, then we have this answer for phi and psi. Is it correct? No, because if I take different gammas, I have different results. So these numbers cannot be taken seriously. Okay, you have to be careful with this. And Dowling and Massitelli did the following. They said, okay, we have these quantum corrections. We have these corrections to the effective action of gravity with these combinations of beta. But we don't stop on this. We now consider all this related to the mass capital M. And now we take a small mass, m, small m, which will be a test particle. And we will send this test particle to travel in this gravitational field created by our classical source. And then this test particle will give us our potential, which we want. And this works really. So when we insert our terms here with these relations which I gave you before, we have this formula for the divergences in case of test particle. This T is the energy momentum tensor of this our test particle. Here I missed M index, it should be here. And then we take the equation for the test particle. It has classical part plus this gamma 1. Variational derivative of gamma 1 divided by mass because we want unique mass. And this works. So finally, we get this combination. This is this equation gives you acceleration of the particle. Here we use Newton law, second law of Newton, and we say that this is nothing else but the gradient with minus gradient of the corrected Newtonian potential. And by chance, all these dependencies of the gammas and betas in this new parenthesis cancel. So this is a physical result. If we take the number, it is 17 over 20. If you go to Donohue's papers, there is 41 over 30 in this part. And all the fight is because of this condition and because of the approach in general. And remember that numerically, this has extra g divided by r squared. So if we don't go to the Planck layers, this coefficient kills the physical importance of the result completely. Okay, still it's very important because we want, after like 60 years of working on quantum gravity, we want to calculate something and agree. And for me, for instance, it's quite strange that we cannot do it. So the next question is, why this magic combination is gauge fixing independent? We already know why. Because remember this formula from the first lecture of today. So this difference between gammas calculated in different gauge fixings is proportional to the classical equation of motion was multiplied by some coefficient. The classical equation of motion in this case is similar to what we had before, but instead of cosmological constant, this is T min. But it works perfectly well, the logic. So it works very well. So we finally get this, remember this formula for divergences. Remember that f mu is like this, okay? Because we need 4 derivative term, and we already have 2 derivatives in the equations of motion. So 4 minus 2 is 2. So we need f mu, which is quadratic in derivatives, and we have this. If we replace it back to our delta gamma 1 diff, we get this expression. Now we go and once again see how this coefficient C changes. they change in this way as before. So we know that C1, which is Gauss-Bonnet, is invariant, which has no physical consequences at all. And we have this new invariant, C2 plus C3 plus C4 minus 5C plus 4C6. And this exactly gives you this beta invariant. So this guy is invariant not by chance. It's invariant because we have this general theory of quantum field theory that one loop divergence is called what? Yeah, that one loop divergence is on shell, when classical equations of motion are involved, epsilon mu. They do not depend on gauge fixing and parameterization. So this is a very strong theory, okay, and it works. We can check it in many cases, and we can apply it in many cases, and every time it works. So if you one day will get one loop divergences for any theory in non-trivial gauge, in non-trivial parameterization, remember this. This is your main friend, this theory, okay? And it was proved by many people, starting from Arefьева, Slavnov, and Faddeev in '73. So Arefьева is still very active. Organized, by the way, there is a system of international seminars, online seminars of quantum gravity, and Arefьева is the main organizer. Okay, and Slavnov and Faddeev are not available anymore, unfortunately. So you see, we found invariant result for the Newton correction to Newton potential, and we understood why it is invariant. It's invariant because this particular combination is unique, very important. That it's unique combination which is invariant. You cannot have other. So we conclude that this method, which Dalbit and Masitelli suggest, really works, and it works because of this theory of the Arefьева, Faddeev, Slavnov, and Kummer, and Tonin, and Costa and Tonin, and other people who did it after Batalin, Tutin, and so on. So everything fits, everything fits. Now the question is, okay, if we believe to all this, if we do not like to quantize macroscopic bodies, if we want this, if we want to work with this scheme and apply this as the effective quantum gravity, how we can put it to practice? I mean, as I said, corrections to Newton potential is something very interesting, of course, theoretically, but it has only very academic interest because it's 74 orders of magnitude below our abilities. Maybe now with this Southampton new experiment, it will be like 50 orders of magnitude because they have completely unbelievable precision. But still, 50 orders is a lot, okay? So we cannot do it, we cannot do it. And here we have the following interesting, once again, one small observation, which shows more my doubts than certainty. So when we discuss with Donahue all these things, with John Donahue, so he insists that after all, the two approaches can be put together, because he said that when we make this limit, okay, which I show you, which we saw with Wagner in details, actually, in this Antoniadis Matova model, John says that maybe when you take this limit, there are some logarithmic divergences, because remember that there are in this mixed diagrams which he used, there are quadratic divergences and logarithmic divergences. He said maybe part of the logarithmic divergences survive and gives this contribution which kills the difference, and his result becomes correct. Maybe this is correct, maybe this is true, but technically I don't see how it can be true for the following reason. We tried actually, because you see, this is unique combination, unique invariant combination. You cannot have another one because of these formulas. So how it can be that his contributions will give exactly the same? I don't see it, because there are like, if you go to details, it's very difficult to believe this. But in principle, it cannot be ruled out. And this remains an interesting question to solve. Now, this is unpublished response to one of my former student, Actually, I was not his supervisor, but he took 6 semesters with me. David Rodriguez. He asked me how to do this. I did it, and then David said, no, it doesn't work. So, but I started to show it, expecting that somebody will like it and try. So let us think, can we do this in cosmology? Apply this effective method in cosmology? It's quite interesting because cosmology is the main laboratory today. We know that the most important projects in experimental physics are now in observational cosmology. There are big money, a lot of people, most advanced technologies, computer forces, and so on. So, and the precision grows. Every 10 years it grows dramatically. If you take pictures from WMAP and compare them to Planck, you will see the difference. But if you take Planck and compare Hubble and compare to Webb, this new telescope, there is also a big difference. So it grows, it improves and improves and improves. So maybe they will measure something by the end of the day for us. So for poor quantum gravity people. So what we do? Let us take gas which fills the universe without cosmological constant, just for simplicity. This is a small example which shows what we can expect. So, and we assume that this gas is made from particles. It means that these squares of the AM matrix or T matrix are exactly the same as for individual particles, right? Because if there are two particles in different places, the average will give you 0. So let us assume that we can use these formulas. This is not obvious at all, I would say. That's why I didn't publish it. But then we get this expression, as we know. Okay, and if we use on-shell conditions here, that means that you apply our invariant combination, then we come to this formula. And this formula is quite interesting. Why? Because it means that the invariant effective quantum gravity contribution to the gas of particles gives you product of 2 traces of energy momentum tensor multiplied by this log. Log is not relevant here, certainly, because log has, of course, you see, if you have a cosmological metric, this means you have box is something like if you have G mu equals to exponential of 2 sigma of eta, eta is conformal time, and then you have eta. Let's take simple case when this metric is flat. Then box is exponential of minus 2 sigma, right? Multiplied by box point is flat Minkowski, plus something. So log of box, okay, is proportional to minus 2 sigma, which means minus 2 log A. A is the conformal factor of the metric, log A of t. And log A of t is a slowly varying function. So if you take a particular class of phenomena in cosmology, for example, you take inflation, okay, even when things develop very fast, but you are interested in the development of cosmic perturbations, then you perfectly well can think that log A is a constant. Then you see that quantum gravity produces T square. And T square is something non-trivial, you know, because there are many cosmologists working with T square gravity. I am editor of the journal, and I receive every month, I receive papers when poor people put T square to their action and try to solve one or another cosmological problem. And they just take it from their head. And we can say that this is the result of our quantum gravity contributions, effective quantum gravity contributions. Of course, there is a subtle point. You see here is kappa square and kappa 4. Kappa 4 means 1 over Planck mass 4. So this product is suppressed. This is true. But the T can be big, so in some epoch of the universe. So in principle, this is quite remarkable. I think that we have a chance, let's put it like that, to get something non-trivial for cosmology like T squared from effective quantum gravity. And this is well-defined correction mathematically. Mathematically, it's well-defined correction. So I leave it to you, so you can try to think about this. And so I basically finished. So we can go to first set of conclusions. So what is effective quantum gravity? Effective quantum gravity is a huge simplification. Remember, our initial purpose was to find singularities and deal with high energy things to improve gravity. At low energies, we don't need to improve gravity. Gravity is perfect. Einstein gravity is very, very good theory in low energies. So we wanted to have gravity for which is free of singularities. When we go to effective quantum gravity choice, it means that we give up from this. We say, okay, we are poor people, we don't like this. We want something small, maybe irrelevant. We agree with that. We want to calculate something, and this something has to be well defined. Okay, very good. Then we give up from the describing quantum gravity as a fundamental theory, singularities and things like that. So, what we can calculate, if you take this effective quantum gravity section, you see that people calculate different things. But the most traditional object to calculate is quantum correction to Newtonian potential. And this is what Donahue did in his seminal paper. And yeah, it was 30 years ago. So you see that here, even in this, let's say, modest approach, which has nothing to do with Leonardo Modesta, who is a good friend of mine, but I would say he is not very modest. So, yeah, he deserves it. But anyway, so you see, even with this very, very modest approach, we cannot calculate something and be sure that this is well calculated, okay? Because we have disagreement between different groups. If we draw the diagrams with internal lines of macroscopic bodies, then we have the problem which was solved by David and Massitelli in 1997. And we know that this means that we go on shell is equivalent to going on shell for quantum gravity corrections and also going on shell for the test particles. And then we get a real correction to the Newtonian potential. One very interesting thing to do here, which nobody did as far as I know, would be to consider the case when this test particle is not static. Because all this corresponds to the static limit. You can try to go beyond static limit. Okay, some people already asking me whether it would be interesting. I say, okay, sure. And yeah, and unfortunately, for the Newtonian force, the numerical effect is very small. So phenomenologically, it has very small importance. And since it is the last lecture, let me give very short general conclusions. So we know from the first lecture that higher derivatives cannot be avoided at quantum level. There is no way to do it, even string theory. It solves it, but it solves it in such a way that we don't like it too much. Then, in principle, you can solve the problem if you assume that there is a cutoff on the energy density of gravitons. And the origin of this cutoff, or at least of the Planck order or a little bit below. And this can be explained by forming bound states from the ghost in the 6 plus derivative gravity. So you need 6 derivatives, 10 derivatives, 14 derivatives, and so on. So if you have this theory, there is a chance to have bound states and avoid problems with ghosts. Now, if we go to effective approach, it's going to be very successful because you don't care about ultraviolet divergences and you have some reasons, regardless it was never proved that completely I say, but we have very good reasons to believe that quantum gravity based on relativity is the universal infinite quantum gravity. And finally, the main question, can we check something in quantum gravity on experiments? And the answer is that no. Okay, so is it just empty exercise without perspective? Also no, because if today we don't have perspective, maybe we will have it tomorrow. For example, the presence of cutoff in the density of perturbations, cosmic perturbations, okay, in principle can be observed. Okay, And some those cosmologists who work with perturbations, they know that in principle the initial spectrum of perturbations can be or bunch Davis vacuum, which is a standard assumption, or some modified version. Maybe and looking how it develops experimentally, observationally, maybe in some decades they will measure something interesting for us. Okay, so in principle, this I would say this is the only chance. This is the only chance, at least for today. And here I stop. Thank you very much for the invitation once again.
Now we have time for a few questions. Professor?
There is this, I don't know if it's yet, it happened already, but there is this very precise experiment of measuring the gravitational potential between two very close objects to see if there is a small deviation from 1/r. So could this be used to?
I don't know that. You know, I know that they measure gravitational Newton force between two masses in small distances. Moreover, I don't know this only from boarding, because 12 years ago I gave a short course also, more or less, but with chalk, because they told me before that I don't have that what they want. Yeah, but it was in Bloomington, Indiana, and they took me on excursion. The guy called Josh took me for excursion to the laboratory. I did not understand this important moment in my life, and he showed me the laboratory. It is far from all installations because he needs a very silent place. It's a small house. It's like 3 by 3 meters. It's his laboratory. When he measured and published in Nature, if I'm not wrong, the Newton law to the micrometer
I think there's
scale.
a generation of this. That it's
Yeah, there are several. But I was in one of these laboratories, and I even touched the device, and then I understood that I shouldn't do it. so it means that, remember, if there are old people like me, you probably remember that in '92 there was a paper by Antoniadis, Dimopoulos, Dvali, and somebody else saying that there may be sub-millimeter non-complete compactification from string theory, and this changed the Newton law at the distance of 10 minus 1 0.1 millimeter. So Josh in this laboratory ended this. So after this laboratory experiment, you don't need to worry that in CERN you can produce black hole. Remember, there were crazy people saying that CERN must be closed because they will make a black hole will eat all of us. This was never serious because from the cosmic rays you get protons, which are like 10 million times more energy than the protons in LHC. still, Josh in this small laboratory, 3 by 3 meters, finished this. So you know that the Newton law works very well to much smaller distances. Okay, but for the two plates, I don't know. Maybe you can ask Josh and he, okay, or somebody else.
Because my question was if any of these could be tested with these very small distance.
70. David, his reaction to this paper of Donahue was that you know that there is 74 orders of magnitude between your result. This actually, I think Donahue at that time was agreed very fast that this p-type terms should be disregarded. But then David asked, you are from standard model, would you worry if somebody calculates something which is 10 minus 74? And Donahue responded, not of course. so 74 times, you know, no experiment, unfortunately. And the reason is that this force power of the Planck mass is the denominator. Why it is difficult to detect gravitational waves? Why is this LIGO and Virgo and so on struggle so much? Because when you emit gravitational wave, you have 1 over Planck mass squared in the denominator, and when you receive it, you have another one. So you need like crazy event, like matter of two black holes emitting solar mass of in gravitational waves, which is completely unbelievable quantity of energy. Okay, then you can detect it. So not something macroscopic, normal macroscopic. Okay, it's gravitational physics is like that. Okay.
Perfect. No more questions? So for the final class, I thought for organization, would you like to give you this present, Professor?
We'll see.
A present. It's a surprise.
Okay, thank you very much.
Yes.